Hello and welcome to your preview of Training to Go modules presented by Technical Sales and Consulting. This preview covers power factor correction and power flow. It is extracted from our power management course. At the end, we will provide how to access more information about our training products. Thanks for visiting and we hope you enjoyed the preview. For more information visit our website trainingtogo.net. The average power factor for an AC motor is typically around 0.85 at full load, but can vary depending on the motor design, load conditions, and can drop significantly at low loads, sometimes as low as 0.20 when the motor is not heavily loaded, making it important to consider load when calculating power factor for an AC motor. A perfect power factor is 1.0, where all the power is used efficiently. Unfortunately, due to design constraints, motor manufacturers cannot build motors with unity power factor. The inherent design of the induction motor does not allow this to happen. Most utilities typically require a power factor level between 0.90 and 0.95 from their commercial customers, meaning if a customer's power factor falls below this range, they are subject to additional charges on their electricity bill. The extra charge is based on how much their power factor deviates from the required level. This is known as a power factor penalty. Here is why it matters to the utility. A low power factor means more current is needed to deliver the same amount of power, causing inefficiencies in the power grid and higher costs for the utility. Let's see how the power factor is determined. The formula for power factor is, power factor, PF, equals real power, kW, divided by apparent power, kVA. Essentially, it is the ratio of the actual usable power to the total power drawn in a circuit. Here are some key points about the power factor formula. Real power, kW, represents the power that actually does work in a circuit. Apparent power, kVA, represents the total power drawn by a circuit, including both real power and reactive power. In technical terms, power factor can also be calculated as the cosine of the phase angle between the voltage and current in a circuit. It is represented by this triangle. Note apparent power kVA or kilovolt amperes is represented on this axis. Real power kW or kilowatts represented here and reactive power kVAR or kilovolt amperes reactive represented here. Since everybody likes beer, perhaps this can better illustrate the concept. The entire mug of beer represents the total demand power. The foam represents the wasted power and the amber fluid becomes the useful power. Now what can be done to improve power factor? Well, there are two widely used methods. One is to connect the capacitor to a single motor as seen here. It can be installed in any of these three locations. If it is a new motor installation, the capacitor can be placed in position A, on the motor side of the overload relay. Position B is used if it is an existing motor. Position C is used when a reversing, multi-speed, or frequenting starting motor is used. Capacitor manufacturers provide tables to select the capacitor based on motor horsepower and speeds. Here is an extract from a table showing motor speeds of 3,600 rpm. Note the columns for horsepower, kVAR and percent correction. The second location is used when connecting entire plant loads as seen in this image. Capacitor banks can be installed at the service entrance. When this method is preferred, capacitor manufacturers provide a table seen here to help with a calculation that starts with the existing to desired power factor. Let's zoom in on some of the columns to see the numbers. For example, find 0.57 in column 1. Then go across to 0.95. That shows a value of 0.822. Then multiply that number times the kW demand. Then round the number and you will have the required kVA or capacitor rating for installing at the incoming service. In summary, power factor correction capacitors can provide improvements to the power system while saving on the energy bill. Finally, an excellent resource is a publication from Eaton called Power Factor Correction, a guide for the plant engineer technical data SA 02607001E. Power flow goes hand in hand with power quality, and a good examination from incoming service to branches and loads is crucial for power system efficiency. Let's go over the areas covered with a power flow study. At the beginning of the study, engineers will do an overview of the power system. A power system design review ensures that an electrical system meets operational, reliability, and safety standards. It evaluates factors like load distribution, redundancy, and system efficiency. The method for studying is to conduct single-line diagram analysis to verify proper component ratings. Next, use simulation tools like ETAP Electrical Transient and Analysis Program and PSS/E Power System Simulator for engineering to model system performance under normal and contingency conditions. It is also important to perform short-circuit and protective device coordination studies to ensure proper fault protection. These actions can provide potential solutions that include upgrades to outdated components like conductors, transformers, and circuit breakers. The review might also indicate a need to optimize system redundancy to improve reliability. One last outcome could reveal that the trip settings on certain circuit breakers be adjusted to ensure that the breaker closest to the fault trips first. Energy management focuses on optimizing electricity consumption while maintaining reliability and reducing costs. It involves monitoring, controlling, and optimizing power use across a facility. The method for studying involves using real-time energy monitoring systems to analyze consumption patterns. It is necessary to conduct energy audits for identifying inefficiencies. Examining peak demand is useful for providing information to implement demand response programs and balancing loads. Potential solutions are to integrate smart meters for accurate data collection. Manage energy-intensive processes by using automated control systems. Investigate the use of renewable energy integration to reduce dependency on grid power. Load flow analysis determines how power is distributed across an electrical network. It helps in optimizing voltage profiles, reducing losses, and preventing overloads. There are a few methods for studying. One is to use power flow simulation software like PowerWorld, DigSilent to calculate bus voltages, line losses, and power distribution. Performing N1 contingency analysis to assess system ability to withstand a loss and what backup is available. Evaluate voltage stability margins to prevent system collapse. Potential solutions include adjusting tap settings on transformers to regulate voltage. Optimizing reactive power compensation to improve voltage profiles. Power factor correction improves system efficiency by reducing reactive power demand, lowering energy losses, and avoiding penalty charges from utilities. Part of the power flow study will measure power factor and reactive power demand using power quality analyzers. It will also analyze load types, inductive, capacitive, resistive, to determine correction needs and simulate capacitor bank placement to optimize correction. The potential solutions might recommend installation of capacitor banks or synchronous condensers for reactive power compensation. It could reveal the use active power factor correction devices in variable loads. Lastly, an outcome could be to adjust motor loading and replace inefficient motors with energy-efficient models. Motor starting analysis helps prevent voltage dips, inrush current issues, and mechanical stress during motor operation. Large motors can impact system stability if not properly managed. Larger motors can also have an effect on demand charges on the utility bill. These are the items that the study should include. Measure inrush current profiles using high-speed power monitors. Simulate motor starting scenarios in power system analysis software. Analyze voltage dip and recovery time at different buses. Examine utility bills to develop a history of high demand times. Here are some potential solutions. The use of soft starters or variable frequency drives to control acceleration and reduce demand. Implement staggered motor starting to reduce simultaneous high current draw. Upgrade transformer and feeder capacity if voltage drops exceed permissible limits. A well-conducted power flow study ensures a reliable, efficient, and stable electrical network. By leveraging modern simulation tools and best practices, power systems can be optimized for both current and future demands. Hi, we hope you enjoyed the sample video of our online e-learning module. This clip is from one of our many available modules. We are always working on new modules. Here is the current list of developed lessons. Did you know that 16 of our courses carry 22 NETA CTD credits, and we have courses suitable for Pennsylvania and Delaware CEU credit? New modules are being constantly added, so check back with us on our website trainingtogo.net. Let our Training to Go programs train your people while you run your business.